Okay. So last class, we introduced the notion of renormalization group flow. And what I wanted to do today was to try and make precise a few of the notions that we introduced last class involving flows in the space of couplings in quantum field theory as you vary the energy scale at which you study the quantum field theory. So this is a notion that goes under the name of renormalization group flow or Wilsonian renormalization. And I'd like to begin just by reviewing very briefly what we mean when we talk about Wilsonian renormalization before working out one specific example, that's scalar phi-4 theory, in a bit more detail. Okay. So let me just remind you of what we discussed last time. So let's imagine that we're studying some quantum field theory. And this quantum field theory is defined up to some UV cutoff scale that we'll call lambda. So for example, you could imagine that this quantum field theory, say, describes quantum electrodynamics up to some cutoff scale, where that cutoff scale is where some sort of new physics involving electroweak forces or nuclear forces or something like that becomes relevant. Or you could imagine that this is a quantum field theory describing the phonon excitations of some material, and there the UV cutoff scale might be the lattice scale associated with the spacing between the atoms in that material. But essentially, we wish to study the quantum field theory intrinsically defined with this UV cutoff scale. And we're going to be interested in computing observables, such as correlation functions of fields, with momentum scales that are much less than that UV cutoff scale, lambda. So we'll say observables with momenta less than b lambda, where b is some number that is less than 1. In principle, say if you're studying materials physics, where lambda is set by the atomic spacing scale, b could be much, much less than 1. And the idea is that as we integrate out in a way that we'll be making precise a little later on in this class, the degrees of freedom at very high energy, so the ultraviolet degrees of freedom, so those correspond to field modes with momentum bigger than b lambda. The effective coupling constants of the theory that we use to describe the infrared physics will change. And they'll change because of interactions between the infrared degrees of freedom, the low energy degrees of freedom, and the ultraviolet degrees of freedom. So we studied this a bit schematically last time, and we saw, roughly speaking, that in the infrared, those coefficients, those couplings which have a positive mass dimension become more and more important at low energy, and those couplings that have a negative mass dimension become less important at low energy. And today what I want to do is work out one very specific example in more detail where we can make all of this much more precise. Okay. So let's consider scalar phi-4 theory. So the Lagrangian, the full Lagrangian of the theory, defined in terms of all field degrees of freedom up to the cutoff scale lambda, is going to be given by our familiar Lagrangian. So there'll be some kinetic term, a mass term, along with a term describing the phi-4 coupling. So here, phi is the physical field, and the coupling constants m and lambda that I've written here are the physical mass and 4-point coupling. And because of that, I need to include these wave function renormalization factors, z lambda, zm, and z phi, which relate the bare quantities that appear in the Lagrangian, the coefficients of d phi squared and so forth, to the renormalized values. So for example, z phi compared to what we wrote earlier would be 1 plus some counter term that is of order quadratic in the coupling constant lambda. M phi, or Zm, is 1 plus some mass renormalization term, and likewise for Z lambda. And these coupling constants M and lambda are defined at some infrared scale. So for example, the easiest way to define the physical coupling lambda is that it's the 4-point function at very low energy. Okay. So here M4, I'm just denoting by the 4-point function, the exact 4-point function summed over all Feynman diagrams, with all of the external momenta, P1, P2, P3, and P4, set equal to 0. Okay. So this is a perfectly good definition of what we mean by the physical coupling. It's just the phi to phi scattering amplitude at very low energy. And in order to compute observables, we need to compute the partition function, which is a function of the source J, that is given by a path integral. So let me write it like this. So it's the integral over all field modes, phi, times e to the is plus the integral of j times phi. And it turns out that in order to actually study this path integral precisely, what one needs to do is perform a Wick rotation. So we're actually going to be performing this path integral, although not terribly explicitly, but at least implicitly. And we'll do it as we have done before in the computation of loop integrals, by going to Euclidean signature, by which I mean we make a change of coordinates where we define a so-called Euclidean time, t sub Euclidean, that is I times the usual Lorentzian time, and then we write our action as a Euclidean action that is an integral over the 4 Euclidean directions, so d3x and dt Euclidean, of some Euclidean Lagrangian, so that the total partition function will take the form of the integral d phi of lambda e to the minus s rather than e to the is, plus this coupling term j phi. And then you can go ahead and, I believe this is something that we did already, at least implicitly, and compute the Euclidean Lagrangian. So what is it? Well, it's just exactly what you would expect when you make a change of coordinates where t picks up a factor of I. So it goes like 1/2 z phi times d phi by dt Euclidean squared plus the gradient of phi squared, rather than minus the gradient of phi squared, plus the various coupling terms, the mass term, and so forth. And the point of this Euclidean continuation is that now in Euclidean signature, these two terms are both positive definite. Recall that in Lorentzian signature, you have minus phi dot squared plus the gradient of phi squared. So that means that if you imagine doing this integral, say this integral right here, then you could certainly have solutions where, say, the gradient of phi is very large, or the or phi dot is very large, and these would give you rapidly fluctuating contributions to the partition function. And these are a little bit tricky to deal with. One has to remember I epsilon prescriptions and stuff like that in order to deal with them. So a technical trick that we often use in order to make the partition function simpler is just to make this change of variables to Euclidean signature. And in that case, if you stare at this expression for the partition function long enough, you'll see that this is something that's obviously nice and convergent. So first of all, the factor of I has disappeared here, which means that there's nothing that's oscillating rapidly. And moreover, it's e to the minus s, where s is a positive definite quantity. Okay? And the reason being that you have a sum of two squares here, rather than in Lorentzian signature where you have the difference of two squares. And so if you want to think about this integral, it's really something like a Gaussian integral, at least when you include just that kinetic term. And the sign here, the sign right here, guarantees you that it's a right sign Gaussian integral. It's like an integral dx of e to the minus x squared rather than e to the plus x squared. Whereas this integral that you have right here is a little bit like the integral e to the I x squared, which is a bit harder to make sense of unless you include some very careful discussion of a contour prescription. So right now I want you to think about this Euclidean path integral just as a technical trick in order to make these integrals better defined. Now when you consider the relationship between quantum field theory and statistical mechanics, it'll actually turn out that these Euclidean path integrals are not just things that you use for technical reasons. They're actually literally partition functions of statistical mechanical systems. Okay. That's something that you'll be seeing at least a little bit on the problem set that you're doing this week, or rather, the problem set that I just handed out. And it's something that I think I need to go through the schedule for the class and decide if we have enough time, but I think I might try and spend at least a lecture or two on maybe next week. Yes, there's a question.
Also the same with ZF, it seems like, or not?
Yeah, I mean, I suppose, yeah, I guess you need to decide whether you have an I there or not. I have been a little sloppy with that. I suppose, technically speaking, I usually put an I here. And then that I would go away when you go to Euclidean signature, because this measure factor here includes an integral dt Euclidean, which has a factor of I in it compared to the Lorentzian one. Good question. Remember, I think we did define an I in that coupling term, so that to calculate a correlation function, you take I times d by dj, if I remember correctly. In any case, that's just a definition, so that's not something you should worry about too much. Any questions on this? I mean, the nice thing is that there's no factors of I in this path integral, so it's really just like doing a Gaussian integral. In fact, I mean, if you want to make that a little bit more explicit, that's easier to understand in momentum space. So in momentum space, so if you define the Fourier mode of your field as an e to the I kx times 5x, then the Euclidean action, well, what does it look like? Well, the kinetic term is just going to be something like the integral d4k times phi of k times, what was it? So this was a Lagrangian. If you just write that down in momentum space, you'll get a z phi times k squared plus zm times m squared times phi of minus k. That's the kinetic term. So in order to get that from from this Lagrangian up here, all I did is I inserted the Fourier expansion for phi, and then I used, so that gives you two integrals dx, two integrals dk. When you write phi of x as the integral dk, e to the I kx phi of k. And then I used the x integral to give me a delta function that I used to do one of the k integrals. And then that set the two k's, we could call them k1 and k2, equal to minus one another. So that gives you this expression that I've written here for the kinetic term in Fourier space. And then, for example, if we wanted to write down the interaction terms, they're somewhat more complicated, so they would involve, say, 4 phi's. So 4 k's, integral d4, k1, k2, k3, k4, along with a momentum-conserving delta function that comes from the x integral, and then 4 powers of k. So 5k1, 5k2, 5k3, 5k4. And so you can see that if you think about this in momentum space, then at least this kinetic term, it's just literally one Gaussian integral for each momentum mode k. Is that clear? I mean, we sort of did this last semester, but I guess it's always worth taking a look at again. And then the basic idea of renormalization is that we want to split up the path integral for the partition function. So z was the integral d phi e to the minus s Euclidean plus j phi. We want to split that path integral into 2 parts. So in particular, what we want to do is think about the integral over all field modes as an integral first over the modes in the infrared, and then an integral over the modes in the ultraviolet. Okay. Where here the infrared modes describe those field variables phi of k, where k is less than b lambda, and these describe the integral over all of the field modes in momentum space with k bigger than b lambda. And here I've included a cutoff lambda so that it will only take k to run from b lambda up to lambda. I mean, so this is the sort of computation that we at least imagined doing last time. And now I'm going to actually do the computation for you explicitly. But before I do so, let me pause and see if there are any questions. Yes?
You mentioned that action is positive definite function, but once we do this fourth term,
Yes.
then guarantee this is positive definite.
That's right. That's right. I mean, strictly speaking, path integrals don't exist for precisely this reason. So actually, in phi to the 4 theory, it's not so bad, because as long as the sign of this guy is right, as long as it's a right, as long as the sign of that guy is right, it's still positive definite. But certainly, you know, in general, if you considered, say, phi cubed theory, for example, then that path integral is just strictly speaking not well defined, because you would have, it's like doing the integral e to the minus x squared plus x cubed. That's just not a well-defined integral, unless you define the contour of integration over x very carefully. Okay. So, as usual in quantum field theory, or even in quantum mechanics, we don't try and define what we mean by a path integral too precisely. Okay. It's more of a convenient trick for organizing Feynman diagram expansions in our head. Okay. Although, I mean, I think for phi to the 4 theory, there's no particular reason why you know, you need to be worried about that, because these integrals really are pretty well defined. The problem is not so much an integral at one of the individual Gaussian, or not Gaussian, phi to the 4 integrals, but rather how you regulate doing all of them together and how you take the k goes to infinity limit. And indeed, as we'll see by the end of class today, something goes deeply wrong with the theory if you try and take the cutoff away, if you try and take lambda to infinity. Yeah, so we'll get back to that by the end of class today. Good. Any other questions? Okay. So the idea is that if we're only interested in studying the modes in the infrared, that is to say those modes where the momentum k is less than b lambda, then we should just do the UV part of the path integral. We should just regard z as a quantum field theory but a quantum field theory with only the infrared degrees of freedom. So we do the path integral over the UV degrees of freedom to obtain an effective action that's now a function only of the infrared degrees of freedom. And then the point is that you could go ahead and, once you do this path integral to obtain the effective action, you could treat the effective action just like you would a normal action in quantum field theory, and use that for doing all of your computations of the infrared observables. So here, the effective action is defined to be the integral over the UV degrees of freedom of the full action. And schematically, it'll take the form of the integral of some low-energy effective Lagrangian, which will, well, it'll schematically, any Lagrangian really could be written in the form, so you'll have some quadratic piece along with a mass term, and a quartic coupling term. And then, in general, you could have all sorts of other coupling terms that arise when you do this path integral. Okay. So let's just consider all possible operators that you could have in the theory, that you could add to the Lagrangian. So let's label them, say, by their dimension d, the dimension of the operator, the mass dimension of the operator, along with an index I that labels all the operators of a given dimension. And so we'll just call those operators O sub d comma I, and let's call their coefficients C sub d comma I. And the point then is that, in general, when you do a path integral like this, you should always be able to express the result as e to the integral of some effective action, where that effective action can be some arbitrary function, or rather functional, of the infrared field phi. But the point, the important point, is that the coefficients in that effective action, the things that I've called z sub phi, m squared, lambda, and c here, are now functions of that parameter b, which was related to our choice of which infrared degrees of freedom we want to study. Okay. And as you change b, those values of those parameters are going to change. Okay. So just sort of, for example, the trivial case would be where b is equal to 1. In the case where b is equal to 1, you're not integrating over any of the UV degrees of freedom. And so what I call z phi is the same thing that I called z phi up above. Okay, it's just that z phi. And likewise, m squared of lambda is just zm times the physical mass, and so on and so forth. But as you start integrating out these UV degrees of freedom, the effective value of those couplings is going to change. And we're going to compute how they change in just a second. And more importantly, you also will, in principle, get other sorts of operators appearing in this effective action with some coefficients that will also depend on the scale b. And here, as I said, this is a sum over all operators in the theory. And I've specifically singled out here those operators which are relevant, namely those which have a positive or zero mass dimension. Those are the ones that appear on this line up here. As opposed to all other operators in the theory, those which have a mass dimension greater than 4. And I'm using the fact here that because our theory has a symmetry under phi goes to minus phi, you're not actually going to generate any terms which have odd powers of phi. So the first sort of terms that you get here start at dimension 6. Okay, so for example, you'll get terms that look like phi to the 6th. So for example, the first term you might get here might be phi to the 6th, phi to the 8. You might get derivatives of phi and so on and so forth. But the point that I really want to drive home is that this effective action that we're writing down here is really, so that generating function z is really the same generating function as the theory where I include all of the degrees of freedom, infrared and UV. And so if we want to do a computation of, say, some infrared observable, a correlation function, a scattering amplitude, or so forth, we could really either use the full theory where k runs from 0 up to lambda, or we could truncate and use just this effective theory. But we have to use the effective theory with different values of the coupling constants. So we can compute phi infrared up to phi. So a correlation function of a bunch of infrared observables using the usual Feynman rules for the effective Lagrangian. Okay. Because if you look at it here, what is this? This is just a standard. Quantum field theory partition function. But now it's a partition function that only depends on the long wavelength, low energy degrees of freedom. And the price that you pay for that is that you have to consider this effective action S. And indeed, if you think about what we're doing when we study, for example, quantum electrodynamics, is we're not starting with a full UV complete theory of the standard model of particle physics and then computing the anomalous magnetic moment of the electron using that. No, what we're actually doing when we study QED is studying the low energy effective Lagrangian in precisely this sense of quantum electrodynamics. And so what we call the electric charge is really an effective coupling constant in the sense that, say, this L squared and mass are effective coupling constants. Yes, question?
Are you going to do this explicitly? Because this still seems like you're kind of sketching out.
I'm going to do this explicitly. What I'm going to do now is compute these constants. So our goal, then, is to compute. So this is right now just setting up the computation. So let's go ahead and compute these coupling constants. The coupling constants of the IR theory in terms of the UV parameters, which I called z phi with no b, m squared physical, lambda physical, and so forth. Okay. So that's the goal. We want to compute the IR parameters in terms of the UV parameters. Any questions before I do that? Yeah, so here, so I was just so far just setting up the calculation. And the key observation, so it actually sounds like a kind of difficult task to compute these things by doing a path integral. But the key observation, really, is that we can compute these infrared parameters in terms of the UV parameters simply by computing Feynman diagrams with the full UV Euclidean action using your infrared fields, those with k less than b lambda, as your external legs, and only allowing UV degrees of freedom, phi UV with k less than b lambda, to run in loops. I mean, what are we doing here? What am I saying that we're doing? What we're really doing is we're treating phi IR and phi UV as just two different fields. And by integrating out phi UV, what that means is that we want to sum over all possible Feynman diagrams involving phi UV, allowing all of the phi UVs to run in loops. But what we don't want to do is integrate out all of the infrared degrees of freedom. Those are what we're going to use at the end of the day to compute our infrared observables in terms of the parameters in the effective action. So for example, so let's imagine computing the coefficient let's call it C sub 2n of phi to the 2n. We only get even powers because of the phi to minus phi symmetry. So what is that? Well, what you need to do is consider a Feynman diagram where you have n external legs, or let's say 2n external legs, and then you sum over all possible contributions to that using the Feynman rules for your theory, where you treat phi IR and phi UV as independent fields. So for example, at leading order, what is this given by? This is given by a diagram, say, where you have, so let me just draw the diagram for, say, phi to the 8th. So that's what the diagram looks like. You have 8 external legs of phi infrared. So here the solid line denotes an external leg of phi infrared. And the dotted line here denotes a loop of phi UV. I mean, the point being that I'm using the fact that any infrared observable that you can compute, you can either compute it using the effective action S effective, where you only integrate over IR degrees of freedom, or I could compute it using the full S for all of the infrared and UV degrees of freedom. So that means that the coefficient C sub 2n of the infrared theory has to be given by, well, whatever it needs to be in order to reproduce the answer that you would get if you just used the full action for all of the degrees of freedom, where k goes from 0 up to lambda. Is that clear, more or less? More or less? Okay, are there any questions on that? I mean, it's sort of an important point. The important point is that, I mean, I'm being a little bit sneaky here. You know, the important point is that I could, for example, compute, say, the 8-point function of phi infrared just by taking 8 derivatives of that with respect to j. And then I would get, you know, there would be some Feynman diagram that looks like this. That contributes to that. Okay. That would be a Feynman diagram that contributes to that. And I'd have to integrate that loop momentum over all values of momentum, 0 up to lambda. Now, if I want to compute the effective, if I want to imagine only integrating out part of those degrees of freedom, then I have to restrict the range of integration of that loop momentum. So it only runs over the UV degrees of freedom. So the momentum only runs from B lambda up to lambda. Okay. So for example, this would be, so you would get some coupling constant. Well, it would be coupling constant to the 8 in this case, and coupling constant to the n if you're computing the coefficient of phi to the 2n. And then there would be some symmetry factor, which one could work out just by staring at that diagram. I don't think I'll bother to do that. And then you have to integrate over the loop momentum, d4k, and then you have, well, you have n propagators, so you have 1 over k squared plus m squared. And that quantity in parentheses out front is some symmetry factor. I think it's like 1 over 2 to the n, because you have all the different ways that you can permute the pairs of vertices there. But that's not going to be so important for the final answer. Any questions on that? Okay. So, in order to make my life simple, let's just take the case where the mass of the field that we're considering is very small compared to b lambda. So that you can essentially neglect it in this integral. So then we see that this C2n goes like lambda to the n. Then we just get to evaluate this integral. It's just an integral d4k over k to the 2n. And there'll be some numerical constant that I'm not going to worry about too much. But what do you get? You get b lambda to the 4 minus 2n minus lambda to the 4 minus 2n. The point being that because b is less than 1, this first term here is going to be large. Remember, n is bigger than 2, so that coefficient is negative. So this first term dominates. And really that arises because this integral is dominated by the infrared portion, so k near b lambda, part of the momentum integral. And this is a general fact. Okay, it's because we're considering operators that are irrelevant. So the coefficient of irrelevant operators will be dominated by the infrared part of a loop integral. Any questions on this? Yes.
How do you kind of propagate the same equation?
Yeah, yes. I mean, what I'm doing here is I'm computing this coupling constant by looking at this diagram when all of the external momenta are going to be very small. So that all of the internal propagators are just k squared plus m squared. Of course, I mean, that's just sort of a choice of how I define my coupling constant c, if you like. In the same way that the coupling constant lambda was defined by the 4-point function when all of the external momenta were very small. Yes.
How do you determine whether an operator is relevant?
Remember, last time we defined an operator as relevant to be one where the mass dimension of the operator is positive, and an operator to be irrelevant as one when the mass dimension of the operator was negative. The mass dimension of a scalar field in d dimensions is d minus 2 over 2. So in 4 dimensions, the phi to the 4, so remember, the phi to the 4 interaction is the one that's marginal, is right on the cusp between being relevant and irrelevant. Phi to the 6th is irrelevant, phi squared is relevant, and so on and so forth.
It's greater or less.
That's right. Yes. Other way around. Right. In
You said if it's greater than or less than.
D, what did I sorry. 0. Sorry. The coupling constant has to have dimension greater than or less than 0. The dimension of the operator has to be greater than or less than 0. Sorry about that. Sorry, is that clear? I mean, the phi to the 4 interaction is marginal because the coupling constant lambda has dimension 0. The phi squared interaction is relevant because the coupling constant m squared has positive mass dimension. The phi to the 6th operator is irrelevant because its coupling constant, whatever you want to call it, I think I called it C6 here, is going to have dimensions 1 over mass squared. Yeah. Sorry, I misspoke there. Good. Yes?
Could you just explain one more time what you're doing with the diagram that you have up at the bottom of
This page here, this diagram here, that
or even above it, where you
Okay.
have
this diagram here.
Yeah.
Okay. I mean, the idea is the following. The idea is that there are two different ways of computing the same quantity. One way of computing the say 8-point function of phi would be to work with the UV Lagrangian and the UV theory and write down all the Feynman diagrams of that theory. Another way of computing the 8-point function of phi would be to work with the low energy effective action. And they have to give you the same answer, because that's the definition of the low energy effective action. Okay. So that means that anything that came from a loop integral over the UV degrees of freedom, when you compute it using the UV action, has to come not from an integral over the UV degrees of freedom of the effective action, because there aren't any UV degrees of freedom in the effective action, but it has to come from what you would call a tree-level contribution to the 8-point function in the effective action. That is to say, it has to come from this coefficient C sub 8. And so I'm just defining C sub 8 so that the tree-level thing that you get from S effective is what looks like the one-loop contribution when you compute it using the full S. I mean, it's sort of a sneaky trick, but it's really kind of the definition of the low energy effective action. It's the thing that incorporates all of the loop effects that you integrate out of the UV degrees of freedom. Good. And the important point is that because phi to the 8th is an irrelevant operator, the UV degrees of freedom don't actually matter in the computation of C, because the integral is dominated by things in the infrared. Good. Any other questions? Yeah, I mean, it's a kind of tricky, I mean, it's a simple argument, but it's a very tricky one. Okay. So, the other coefficients, say m squared of b and lambda of b, the couplings of the low energy effective theory for the relevant operators as opposed to the irrelevant operators, are actually going to have the opposite property. So the couplings for the irrelevant operators were dominated by the infrared part of a loop integral, and the couplings for the relevant operators are going to be dominated by the UV part of the integral. So, for example, so the 4-point function of the effective action at low energy, well, it has to be given by, well, it's got a tree-level contribution, which was z lambda physical, so that's just the tree-level contribution. Lambda physical, remember, is the physical value of the 4-point function. And z lambda physical was that thing including the coupling constant renormalization, namely the 4-point function counter terms. And then there'll be a one-loop contribution, so which will go like lambda phi squared. So that's, you know, in the Feynman diagram expansion, that's this guy. And then at one loop, I think this is the loop diagram, the very first loop diagram we computed this semester. So there's that loop diagram. Except just as above, we only want to integrate out the UV degrees of freedom. Okay, so I'll put a dashed line there. So you'll get an integral d4k, where now the momentum only runs from b lambda up to lambda, of 1 over k squared plus m physical squared, quantity squared, because I have two propagators. And again, I'm using the fact that my physical 4-point function is defined when all of the external momenta are equal to 0. So there's no external momenta that I have to worry about in this diagram. It makes this integral very easy to do. Okay. So one of the things that you can see is that this is now a logarithmically divergent integral. And in fact, to deal with this integral, what I want to do is I want to use a bit of a trick. Okay, so this is a kind of clever trick. What I want to do is I want to use the fact that lambda physical is computed in exactly the same way by including all degrees of freedom, not just the UV degrees of freedom. So that is to say, lambda physical is equal to z lambda physical plus lambda physical squared times the integral from 0 up to lambda d4k 1 over k squared plus m physical squared. And that means that I could rewrite my integral for lambda of b just by subtracting these two equations. And you would cancel out the UV divergence at large lambda. I mean, maybe it's worth commenting on this expression for a second. I mean, this expression here is something that we've encountered before. This is just the expression that defines the counter terms, that is to say, defines the renormalization z lambda as the thing that you need to include in order for the physical coupling to be equal to the 4-point function of low energies. So for example, if we subtract these two equations, you see that lambda of b is equal to lambda physical plus lambda physical squared times the integral, if I did this right, from 0 up to b lambda d4k 1 over k squared plus m physical squared. So, plus dot dot dot. Sort of cute thing about rearranging the integrals this way is that now I'm integrating only over the infrared range of the infrared, not the UV degrees of freedom. And so we could then go ahead and just do that integral. So I said it's logarithmically divergent. It's straightforward enough to do. I'll just tell you what the answer is. So it's lambda physical. Here I actually wrote down the coefficients here. It's sort of an elementary integral to compute. So you get 3 over 16 pi squared, lambda physical squared, and then you get a log, because you have an integral d4k over something that goes like k to the 4th at large k, b lambda over, well, it's a log lambda, and so it has to be, by dimensional analysis, it has to be divided by the only other thing with dimensions of energy in the integral, m physical, and then there's a little constant piece. Okay. Dot, dot, dot. Any questions on that? So it's worth contrasting this to the coupling constant that we computed up above. So for this coupling constant here, we see that this goes to 0 as lambda is taken to be very large, because you have a negative power of lambda. On the other hand, this thing is logarithmically divergent as we take lambda to be very large. And this is related to the fact that lambda is a dimensionless coupling constant. Phi to the 4 is a marginal operator, so it's on the cusp between being relevant and irrelevant, whereas phi to the 8th or phi to the 6th is an irrelevant operator. Any questions on that? Okay, so similarly, we could go ahead and compute the mass. So, for example, recall that the shift in the mass is computed by a one-particle irreducible diagram, which in the present case in phi to the 4th theory would look like this. so that m squared of b, so the shift in the mass is what we call the self-energy in phi to the 4 theory, which is something I think that we also probably computed in the first week or two of this semester. So the shift in the mass is going to be, again, so now be z sub m squared, plus, now you get something linear in lambda, because there's only one coupling constant, an integral from b lambda up to lambda d4k of 1 over k squared minus plus m squared, because we have only one propagator. And I can use exactly the same trick that I used above, where I use the fact that z sub m is defined by an equation that says m phi squared is z sub m phi squared plus this integral from 0 up to lambda, 1 over k squared plus m squared. And so I can then subtract these two. And you see that the mass squared in the effective theory at scale b is given by the physical mass squared plus a correction term. That's an integral from 0 up to b lambda d4k times 1 over k squared plus m squared. Which is going to be quadratically divergent. So this is going to be m phi squared plus lambda physical times some constant times something that goes like b lambda squared plus dot 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 dot. Okay. So the important thing to note that the integral for m squared b appearing up here is going to be dominated by the uv part of the integral. So k of order lambda rather than the IR part of the integral. So k of order b lambda. I sort of used this kind of clever trick here to rewrite it in terms of something that was only an integral when k is going up to b lambda. But if you think of things in terms of the Baire couplings of the theory, as I did up here, then you're going to be dominated by the uv part of the integral. So this is sort of an important point. It's actually a very deep and sort of physically a very important point. So what this means is that the coefficients of relevant operators such as values of masses are naturally set, or that is to say, naturally determined by ultraviolet physics. Now, of course, we fix the physical value of the mass squared in terms of low energy observables, but the point is that if you ever do a loop integral to calculate a correction to this physical mass squared, then just by dimensional analysis, that loop integral is typically going to be dominated by the UV part of the loop integral. So this means that in order for, say, the physical mass squared to be much less than our cutoff scale, there must be some sort of fine-tuning. That is to say, either the value of the mass squared up near the cutoff scale lambda has to be chosen to be very, very small, or in all of your loop corrections to the mass squared, there have to be some miraculous cancellations which keep this physical mass squared small. Now, there's nothing wrong in principle with setting the value of the mass squared up at the cutoff to be very, very small. But let's just say it's an unnatural thing to do, in the sense that if all of the dimensionless constants in your Lagrangian are typically going to be of order 1, then you would expect the order of the mass of the cutoff scale to be of order 1. In the order of mass in units of the cutoff scale up at the cutoff to be of order 1. Then it seems like some very large fine-tuning to set this mass squared to be small. And there's a reason why I bring this up, which is because precisely this fine-tuning appears to be present in the standard model of particle physics. So, in the standard model of particle physics, we do have a scalar field. Okay, it's called the Higgs. And the value of the mass of the Higgs is the scale that sets the masses of all of the elementary particles. Electrons, muons, and so forth. And as far as we can tell, the appropriate cutoff scale for the standard model of particle physics would be the Planck scale. But the Higgs scale is, some 17 orders of magnitude below the Planck scale. So the Higgs mass appears to be fine-tuned to a part, say, in 10 to the 17. So this is actually probably one of the biggest mysteries in sort of particle physics nowadays, at least in phenomenology nowadays. What is the mechanism, or is there a mechanism, that is responsible for this fine-tuning of the Higgs mass? So this sometimes goes under the name of the hierarchy problem. And another way of saying it is that it's the apparent unnaturalness of the fact that the scale of gravitational physics is so much different from the scale of particle physics, electromagnetism, nuclear physics, and so forth. Another way of saying that is that gravity is a very weak force compared to all of the other forces, such as those involved in nuclear physics or in electromagnetism. And that's really just another way of saying that it requires some huge fine-tuning in order to set the value of the Higgs mass to be so small in units. I should make an important point here, which is that this fine-tuning is only present in some sorts of theories. Okay, so if you can find a theory where there's some symmetry which guarantees that your mass squared is equal to 0, then it will not be the case that loop corrections will make it non-zero. So the classic example of this would be a gauge theory. So if you consider a theory, say, of the photon, then gauge invariance forbids a mass term for the photon. And so that will be preserved by loop corrections. It's only if you have a scalar field, like Higgs, where you don't have apparently a symmetry that's protecting you from generating these mass terms. So one of the favorite things that people like to do when trying to solve the hierarchy problem is come up with some fancy symmetry which will protect the Higgs mass from getting loop corrections for those 17 orders of magnitude between, say, scales that we might observe at a particle accelerator today and the Planck mass. So supersymmetry is probably the most well-known example of this. It's a symmetry that's basically designed to ensure that all of the loop corrections to the Higgs mass get canceled out for scales between the Planck scale and whatever the scale of supersymmetry is, which is presumably very close to the particle physics scales that we see today. So, sorry, that was just a little bit of an aside. Maybe I should pause and see if there are any questions about that, though. Yes.
If you take B to 0,
Yes.
then the effect of the constant also may change sign. Does that make sense?
Well, okay. If you take B to 0, like,
Like if you're interested in a very, very soft...
yeah, I mean, you usually don't want to take B to be exactly 0.
Not exactly,
Well,
just very small. So the lambda is less than m.
Yeah.
and the
I mean, you could. There certainly are cases where the signs of coupling constants can change as you scale up, as you look at different energy scales. I mean, so for example, the observed value of the Higgs mass happens to be almost exactly such that if you run up to very high energy, the Higgs potential changes sign at very high energy and appears to become unstable. People have tried to construct models based on this sort of numerology. Yes. I mean, it can be the case that couplings can change sign as you, it usually doesn't happen, but sometimes can happen that couplings change sign as you scale up in energy. I'm not sure, but I'm not sure if I was addressing your question. Okay. So, just to sort of summarize, the basic idea is that we wish to understand how the coupling constants change as the cutoff scale, or as the scale that we're interested in, which I called B, is varied. So up above, I gave you some formulas. Okay, so here was a nice formula. For example, for our coupling constant lambda, and how it varied as B is varied. And typically, what we actually do is we actually characterize the change in the couplings with the energy scale by taking the derivative of lambda with respect to B. So, for example, let me just we saw that lambda of B went like lambda physical plus 3 over 16 pi squared times lambda physical squared times a log of, what was it, B lambda over M physical. So one way of characterizing this is by taking the derivative of this with respect to log B. That has the nice advantage that the dependence on lambda then will actually drop out there. So the derivative of lambda with respect to the logarithmic energy scale, log B, then is equal to 3/16 pi squared times lambda squared. And now, strictly speaking, I have a lambda of B on this side and a lambda physical squared on this side. But lambda physical, if we're working in a perturbative regime where both lambda of B and lambda physical are small, then at leading order, I could replace this by 3 over 16 pi squared times lambda of B squared. So this is then some differential equation that will be obeyed by the coupling as you vary the energy scale at which you wish to measure the coupling, or the energy scale of your effective theory. So a logarithmic derivative for a coupling constant is often referred to as a beta function. So this is usually denoted beta sub lambda. And so in general, for any coupling, say G, that appears in the Lagrangian, beta sub G is defined to be the derivative of that coupling with respect to the logarithmic energy scale. You know, here I've taken B to be a dimensionless number, so it makes sense to talk about the logarithm of a dimensionless number. Very often, people will just refer to the energy scale B lambda and write this as dg by d log mu instead of dg by d log b. Of course, those are exactly the same thing. You know, strictly speaking, you shouldn't talk about the log of a dimensionful quantity. So you know, it's a little confusing to write expressions for log mu, but log mu and log b differ only by a constant, so the logarithmic derivatives are equal. So if you only talk about logarithmic derivatives, then this is a fine thing to study. And so we can summarize our observation about the renormalization group flow of the coupling lambda by the statement that d lambda by d log energy scale is equal to 3 over 16 pi squared times lambda squared, plus higher order in lambda. Actually, I believe it's lambda to the fourth, but that's okay. And one can similarly write down equations for the other coupling constants, the beta function equations for the other coupling constants that we have in our theory. You know, one convenient reason to do so is that if you look at the sort of integrals that we were writing down, then essentially when you take the derivative, say, of this thing with respect to b, then basically that means you don't have to worry about the integral. You just write down the integrand, just by the fundamental theorem of calculus, or whatever that's called. Okay. So let's just stare at this equation for the renormalization group flow of the coupling constant lambda for a second. So the first thing to notice is that this means that lambda increases with energy because of the plus sign in that beta function there. So that means that if you're studying some very low energy theory and it's a very weakly coupled theory, then if you try and just naively extrapolate that up to high energies, then the effective coupling constant of the theory as you go to higher and higher energies will become larger and larger and larger. In other words, if you try and imagine that we have some lambda phi to the fourth theory at low energy that we're studying with some very small value of the coupling constant, and we want to imagine that that came from some theory that went up to very, very high energies that was still lambda phi to the 4, then as you extrapolate to higher and higher energies, the coupling of the UV theory would have to be very large. And in fact, it's easy enough to stare at this equation and calculate exactly how large it is. Okay. So in particular, we can, so let's say if, say at, you know, some IR scale, mu IR, lambda is equal to lambda IR, and then at some UV scale, mu UV, lambda is equal to lambda UV, then you could go ahead and integrate this equation So this is, let's just call that beta of lambda. So the integral, so just rewriting this equation right here, the integral of d log mu is equal to the integral d lambda over beta of lambda. Okay. So this would be an integral from the infrared up to the UV. And so just doing this integral over here, this would just be the log of mu UV over mu IR. So you can see that if this integral diverges, then the coupling constant lambda will have to diverge at some finite value of the UV cutoff. So for example, if the beta function, let's just use, say, the perturbative value of the beta function. Okay, so let's just, so there are really order lambda cubed terms here. But let's just set them to 0 just to get an idea of what this looks like. Then what do you have? You have log mu UV over mu infrared is equal to 16 pi squared over 3 times the integral d lambda over lambda squared from lambda IR to lambda UV, which is 16 pi squared over 3 times 1 over lambda IR minus 1 over lambda UV. So if you imagine that lambda IR is fixed to be some very small number, say at some low energy scale, then lambda UV will go to infinity when mu UV is equal to mu IR times the exponential of 16 pi squared over 3 times lambda IR. So if you were to make a plot of the coupling constant, lambda, as a function of scale, so here you would have some IR scale, and then if, say, the coupling took some small value at this IR scale, then the coupling would diverge at some finite ultraviolet scale. So what does that mean? That means that lambda phi 4 theory cannot, on its own, be an ultraviolet complete theory. By which I mean, if you have some low energy effective theory and you observe a lambda phi 4 interaction with some finite non-zero value of lambda, and you try and extrapolate that up to high energies, and you ask, what kind of ultraviolet quantum field theory could this come from? It can't have come just from lambda phi 4 theory with a different value of the coupling constant. It must have come from some other more complicated theory. So this divergence is actually something that we encountered earlier in the context of QED, where it was referred to as a Landau pole. We saw that quantum electrodynamics also had a similar feature. In that case, the coupling constant that I was considering was not, it was an effective value of the charge defined a little imprecisely. So here I've defined much more precisely exactly what I mean by an effective coupling. And so for example, if you go ahead, and maybe we'll do this at some point, if you were to go ahead and compute the beta function for quantum electrodynamics, the beta function for the electric charge in QED, in exactly the same way that we did here, you would find exactly the same thing. Okay, So just to quote you the result, so for QED, and this is essentially exactly the calculation that we did earlier in January when we were studying the photon self-energy and interpreting that as a renormalization of the electric charge. The beta function for the electric charge was some constant, well, I'll look it up. It was 1 over 16 pi squared, I just looked it up, or 12 pi squared, times E cubed. And this is the thing that, as we observed earlier, leads to a Landau pole for QED. So QED, as well as lambda phi to the fourth theory, both have the property that they can't be ultraviolet complete theories all on their own. Now there's one sort of caveat that I should mention here, which is that we could draw lambda equals 1 somewhere on this diagram. And the calculation that I did for the beta function was something that was valid at small lambda. And I'm taking that answer and I'm extrapolating it up to very high lambda. So in principle, there's, it's possible that you could have some other behavior at high orders in perturbation theory when you study lambda phi to the fourth theory. Unfortunately, because you're working at strong coupling, you can't use a Feynman diagram expansion. So the only way that people study this is numerically. And numerical studies of lambda phi to the fourth theory seem to agree with this picture that you have a Landau pole at a finite value of the energy, but it's still sort of an open problem. And sometimes people use a fancy word for this. This is sometimes referred to as the triviality of lambda phi to the fourth theory. Okay. So people sometimes say that lambda phi to the fourth theory is trivial. I mean, this is not trivial in the usual English usage of the word trivial because it's a hard computation. It's not trivial. It's trivial, if the beta function has this behavior, lambda phi to the fourth theory is trivial in the sense that the only value of a coupling that would make sense all the way up to the UV would be lambda equals to 0. Okay. Because if lambda were equal to 0, then the beta function here would just be equal to 0. Okay. And so it would stay 0 forever. But if lambda is non-zero, then it will start growing. Even if it starts out very small, it'll start growing quadratically as you change the log of the energy scale. And eventually it'll become large, and then some strong coupling dynamics takes over. And presumably, as far as anyone can tell, you get this Landau pole. Okay. I mean, maybe I should just conclude by mentioning that it's interesting to imagine other sorts of behaviors for the beta functions of couplings. So for example, we could ask whether there is a theory with some coupling constant such that beta sub lambda is negative for small lambda. Then that would imply that as you go to higher and higher energies, lambda would just get smaller and smaller and smaller. So if, for example, you had a theory where when you do the calculation at small coupling, the beta function is negative instead of positive, then that would mean that as you try and extrapolate the theory up to higher and higher energy, the coupling constant would get smaller and smaller and smaller. So your perturbative expansion at small coupling would get better and better and better. And then eventually at very high energies, the coupling constant would go to 0, and the theory would essentially become a free theory. So theories like this are known as asymptotically free theories. And the phenomenon by which a negative value of the beta function leads to a free theory in the ultraviolet is known as asymptotic freedom. It turns out that in 4 dimensions, the only asymptotically free theories are gauge theories, and in particular, they're what's known as non-abelian gauge theories. And so it's these non-abelian gauge theories, which are really the only quantum field theories in 4 dimensions that can be self-consistently defined even at very, very high energies. So these are the only theories that can be defined at all energy scales. I suppose there are also some supersymmetric theories where this is true as well. But unless you have, without, the only theories without sort of very special exotic symmetries where this is true are what's known as non-abelian gauge theories. And sort of quite famously, QCD, the theory of the strong interactions, is an example of an asymptotically free theory. And it's this property of asymptotic freedom that makes QCD an effective and useful theory for studying properties of nuclear physics at high energies. Okay, so I feel like this discussion of Wilsonian renormalization and effective field theory has been a little fast, so I'm trying to decide. I might spend another week or so on effective field theory, trying to develop a little bit more intuition for it, especially with regards to condensed matter physics and statistical mechanics, before, after that, moving on to a discussion of non-abelian gauge theory, and then on to a discussion of spontaneous symmetry breaking and the Higgs mechanism. I think that's probably what I'm going to do. What I'm going to need to do is sort of map out how many weeks left I have in this course, because I think I need to cover non-abelian gauge theory, I need to cover the Higgs mechanism, and if I can, I would like to give us another week on studying effective field theory and hopefully some statistical mechanics. So I think what I'm going to try and do is see if I have enough time to do that next week. I guess I've covered a lot this class, so let me just pause here and see if there are any questions before we end. Is this all more or less clear? I mean, all this business of effective actions and beta functions can be a little abstract the first time you see it. And the idea that coupling constants change with scale is a little scary at first. But okay. Don't worry, we'll get a lot of time to become more comfortable with it. Okay, so I think I'll stop here for the day.